so today we'll be doing set theory. This would have been uploaded a lot earlier and I would have done it in the regular drawing format. But then OBS decided to basically be oh such bullshit. So I couldn't do that. And we just have to stick with this because I can't re-record it. Right, so we're just gonna speed run through this topic because it's set theory, it's short. A set is defined to be a collection of objects taken on a well-defined basis. So, for example, the set A is equal to 1, 2, 3, and along with that, an element is basically each member of a set. So for this set, 1 is an element of the set A, or the set 1, 2, 3. Some of the important sets in math are the set of natural numbers, the set of whole numbers, the set of integers, the set of rational numbers, the set of real numbers, the set of complex numbers, and the set of all irrational numbers are set minus q basically. And some of the important sets in set theory itself, the types of sets basically is gonna be the empty set, which is denoted by the symbol phi. It basically represents this and is a subset of every set. There's the singleton set, which is a set that just has one element. There's finite sets that have a finite number of elements in them, a finite natural number of elements in them, and infinite sets, which have an infinite number of sets. There's equivalent sets where the number of elements in each set is the same. This is the sort of thing we denote for the number of elements in a set, right? So since A and B both have 3 elements in them, they're equivalent. And equal sets are sets where they're basically the same number of elements and whatnot, right? So 1 2 1 2, x is equal to y, simple as that. Right, now going over some of the more important parts of set theory, subsets and supersets. So this notation, when looked at in Venn diagram form, basically represents that the set A is a part of the largest set B, or is equal to B, right? So if we take the set A is equal to 1 and 2 and B is equal to 1 2 5 7, we see that the elements of A are also present in B, all of them. So A is a subset of B and will also be a proper subset of B. The difference between a set and a proper set is basically that in a set, in a subset, it's basically going to be like it's either either belongs in there itself, like it's a small part of a larger set, or it is equal to the set itself, right? So in this case it is a proper subset, as in a proper subset it has to be like it is one of the sets is part of the other set, but the both are not exactly equal. That's why you have the little equal to dash over here and you don't over here. That's the difference basically, right? And supersets are pretty similar. They're just kind of the opposites of subsets. When we say A superset B, we're basically trying to say B is a subset of A. It's the same thing. This is the notation again if you need it. We'll be going over subsets of real numbers, which is going to be more useful in the chapter of linear equalities and the notation. We're just basically going to go over that, right? So this is a closed interval, so it's basically these square brackets -1 and 0, and this is basically denoting every real number between -1 and 0, including -1 and 0. There's open intervals where it's saying basically that it's every real number between 0 and -1 over here, for example, without including 0 and -1. There's also semi-closed or semi-open intervals where it's just one square bracket and one closed bracket. Again, you can look here and you can understand that. So in this case it includes -1 but excludes 0, in the other it excludes -1 but includes 0, right? Very simple. There's also the universal set, which contains every element, and every set is said to be a subset of the universal set. Likewise, the empty set is said to be a subset of every single set. The power set is a set that contains every possible combination of elements in a set, right? So when we take the set A is equal to 1 2, the power set of A is basically gonna be the empty set, and then the elements 1 2, and then the set itself 1 2, right? And then there's this longer example for the power set of B, right? It's basically just going through every combination and everything. Now I believe it's the right time to go over the different ways that a set can be denoted. There is the roster form, which basically goes like this. It shows you all of the elements, or at least like the sum of the elements. And from what I've seen, at least, it's most of the times used to notate an answer, technically speaking, and is mostly used for small finite sets. Again, this is just the most case from what I've seen. There's obviously exceptions. And then there's the set builder notation, which would go something like this. These both are examples of the same set. This is just in roster form, and this is in set builder, right? So basically it's going the set A contains all the elements x, where x is equal to 2n minus 1, where n is the set or belongs to the set of all natural numbers. So this is more so useful for showing the connection or basis of selection of all the elements in the set itself. So in this set 1 3 5 7, like, why have we selected it? Because they are all odd natural numbers, basically following the criteria that 2n minus 1, they follow the pattern, so they put in that set, right? And it's most of the times used as a way to notate a question, sort of, so if you have a question in words and everything, you can very well use this to give it a more mathematical notation, so it becomes easier to solve, and is mostly used for infinite sets. Again, where I've said most and mostly, it's mostly used like that. There's certainly exceptions that you will encounter a lot of the times, right? Now let's come on to the somewhat more confusing part, union and intersection. So when we're saying A union B, and this is the part where Venn diagrams become really important, let's draw the little circle A and B. We're assuming they intersect each other, cut through each other, but that's not exactly necessary. It's just easier to see, right? So when we take it like this, what we basically get is that all of the elements in A plus all of the elements in B, right? So these are two sets. So all of the elements from these put together in one set without any repeating elements. So for example, we have the set A has 1 and 2, B has 2 and 3. So A union B is basically going to be 1 2 3, not 1 2 2 3, because 2 is repeated. Now A intersection B is kind of the opposite, right? And in A intersection B, we're basically taking only the common elements. So for this case, again, A intersect B is going to be 2, because that's the only common element the two have. And when you take two sets and A intersect B gives you the result of the empty set, these sets are called disjoint sets. And this basically means that the two sets have no element in common, except the empty set or element or whatever, because that is a subset of every set, right? So you get that. Now let's come on to the idea of set minus. There's going to be two notations that are used often, either the regular A minus B or A set minus B, which is a slash. From what I know, at least, A set minus B is more standard in actual mathematical theorems and whatnot, but A minus B also works out. You will encounter both. So just like a regular subtraction, A minus B is not going to be equal to B minus A. They mean very different things. So when we say A minus B, what we are trying to say, we're taking this set again, what we're trying to say is basically is gonna take the set A, right, the collection set A and set B, and it's gonna subtract all of the elements of set B from set A. Now that sounds a bit confusing.